AQA A-Level Physics Paper 1, 2019 Solutions. Click on the link below to download the paper. So question 1.1. Two isotopes of iodine are 125 iodine 53 and 131 iodine 53. Determine for those two isotopes the difference between the constituents of the nuclei. So we are looking at the constituent of a nucleus will be the protons and neutrons, because in the nucleus you only have protons and neutrons. Protons number is 53 for iodine 125 and 53 for iodine 131. And the neutrons number for iodine 125 is 125 minus 53, so that would be 72. And for the iodine 131 would be 78. So that would be 135 minus 52, because the mass number here is proton plus neutron. So just to point out, this is atomic number, which is the number of protons, and this is mass number, which is number of protons plus neutron. So the question is asking for difference in the constituent. Well, the difference is going to be number of neutrons. The iodine 131 neutrons is 6, so you got 6 more neutrons for iodine 131 compared to iodine 125, but they have same number of protons. So the difference, according to the question, will be this one: 6 more neutrons for iodine 131 compared to iodine 125. Question 1.2. A iodine nuclide undergoes beta minus decay to form a xenon nuclide. State the nuclear number of the xenon nuclide. So what we need to write down is the iodine with the nuclear number of 131, and the number of proton is 53, which is the atomic number, and that is going through a decay emitting beta minus. So you go beta minus 1, 0 minus. If you emitting beta minus, you will have anti-electron neutrino, and you have xenon, and the mass number on the right hand side has to balance the mass number on the left hand side, so you're going to have 131. Likewise, the proton number on the left hand side will balance the proton number on the right hand side. This is minus 1. What can I add to minus 1 to get 53? So it will be 54. So that will be 54. So that's how we work that out. So 54 plus minus 1 is 53. So that's 53 here, 53 there. So that's balanced. So the question is, state the nucleon number of xenon. So the nucleon number of xenon is 131. So 131 is the nuclear number of xenon nuclide, and the mass number, which what you say in chemistry, but in physics we call it nuclear number. So nuclear number is the mass number. So that would be is the mass number, and the mass number is 131. Question 1.3. A 125 iodine nuclide decays by electron capture to form a tellurium nuclide. State two differences between the constituents of the iodine nucleus and the tellurium nucleus it decays into. So we have the iodine as iodine 125. That's the nuclear number, which is the mass number, and the number of proton or the atomic number is 53, and that is capturing an electron. That's an electron, and to then become a tellurium. So 53 minus 1 will be 52, and 125 plus 0 will be 125. And so if you look at the proton number here, we can see the proton number is 53 and the neutron number is 72. So proton number for tellurium is 52 and the neutron number N is going to be 73. So tellurium has one more neutron than the iodine 125. Tellurium has one less proton than the iodine 125. Question 1.4. Interconversion is a process in which a nucleus in an excited state can release its excess energy. In interconversion, all the excess energy is transferred from the nucleus to an orbital electron through the electromagnetic force. These orbital electrons is ejected from the atom. The tellurium nucleus formed in question 1.3 is in an excited state and can undergo interconversion. Discuss three differences between interconversion and beta minus decay. For internal conversion, only electron is released, but for beta minus decay, electron and anti-electron neutrino released. Internal conversion, all electrons released will have similar or discrete energy momenta. So they will have same or similar energy. But for beta decay, electrons will have a range of energies. Internal conversion, no change in constituents of nucleus. Element does not change. But for beta decay, neutron is converted to proton. Interconversion, orbital electron is lost, but for beta decay, electron comes from the nucleus, not from the orbital, so no change in orbital electrons. Internal conversion is mediated by electromagnetic force, a virtual photon, and we can write that as a virtual photon like that, and the beta decay is mediated by weak interaction, that's capital W minus. So any 3 points here, the first one or the second or the third, fourth and fifth, any 3 of them will give you the answer. Question 2.1. Some cars are fitted with a water sensor design to switch on the screen wiper automatically when it rains. A light ray travels from the light emitting diode LED through the first prism and into the windscreen, and the ray is reflected off the surface of the windscreen at point A, B and C, and then passes through the second prism into a detector. Question 2.1 says to suggest how the design ensures that there is no deviation of the ray as it enters the first prism. So the ray have to enter the prism at a perpendicular or the line of normal. So this line is a line of normal. It has to be perpendicular to the surface of the prism. Hence, there will be no deviation and the ray will just go through. So that has to be at 90 degrees. So the ray, this ray here, will enter the prism along the normal line, which means that this will be perpendicular to the prism. Question 2.2. Suggest 2 features of the design that ensures that there is no deviation of the ray as it leaves the first prism and enters the windscreen glass. The first is that the prism material have the same refractive index or optical density as the windscreen glass. The second is that the prism is fitted onto windscreen without gap between the prism and the windscreen. Question 2.3. The refractive index of the windscreen glass is 1.52. Explain why the ray follows the path shown inside the windscreen glass in the figure. Support your answer with a suitable calculation. So we can see what's happening here is that there is total internal reflection. So now what the question is saying is that why do we have total internal reflection there? For a total internal reflection to happen, then this angle must be greater than the critical angle. The angle of incidence must be greater than the critical angle. So we need to show what the angle here will be. This angle here is 45, but we need to find the critical angle first of all. At the critical angle, if we draw the surface, so we have a surface here and a ray of light coming through there. At the critical angle, the light will go in that direction there. It will be parallel there. So that will be critical angle, and the critical angle is what we need to calculate. If the critical angle is basically less than the angle of 45 here, then total internal reflection will happen. So to find the critical angle to the normal, so this is the normal here, and that will be the angle we're looking for, the critical angle. So that angle here, theta critical. So that's what we're looking for. And to do that, so we can call this one the angle 1, and this one is angle 2, which is to the normal here, because this is normal. So if that is normal there, and this one here is the angle. So this one is 2, if you like, and this is 1. And the 1 is our critical angle, and that's 2 is the angle of reflection or refraction. So in this case, reflection. So let's see. So we know that this theta 2 here is 90 degrees, because that's what would happen if you have a critical angle. You get 90 degrees there, and this theta 1 is what we're looking for. And so we can apply Snell's law. That says N1, the refractive index 1, sine theta 1, which is the critical angle we're looking for, and that will be equal to N2, refractive index, and sine angle theta 2. Well, so we know that we know the sine theta 1, that's a critical angle, will be equal to, N2 sine 90 degrees, because that's theta 2 is 90 degrees, divided by N1. And what we now need is the critical angle, because theta 1 is critical angle. So we can say theta critical will be sine to power minus 1, open bracket. Sine 90 is 1, so we know what sine 90 is 1, so that will be N2 over N1. And we know that the refractive index of air is 1, and air glass is 1.5, and so we can say the critical angle here, theta for critical angle, will be equal to sine to power minus 1, N2, that's the refractive index of air, so that's air, and this one is glass, so that will be 1 over 1.52. And if we plug that into the calculator, we get theta critical, which is theta 1, and that equals 41 degrees. As a result, the theta 1 is the angle that we have, 45. The angle that we have is 45, so theta 1 is greater than the critical angle, which is that 45 degrees. This angle here is 45. That's greater than the critical angle, which is 41 degrees. Therefore, the total internal reflection will occur. So that total internal reflection will occur. Let me just put it here. TIR will occur. Question 2.4. When it starts to rain, what droplets form on the outside of the screen as shown here? And the refractive index of water is 1.3. 3. So that means air refractive index with water is 1.33. But we also know that the refractive index of air to glass is 1.52. Explain why the presence of water at A causes the intensity of the light at the detector to decrease. Support your answer with suitable calculations. Some of the light is refracting into the water when they get there, and so less is reflecting back. And that's the problem here, because some of the water is going through the water, so it's refracting into the water, not reflecting, refracting into the water, and some is reflecting back. So it might be better to calculate the critical angle at glass-water boundary. Between glass and water boundary, we need to calculate the critical angle there. So we can use Snell's law, N1 and sine theta 1 will be equal to N2 sine theta 2. So one is for glass and the other is for water. And for the glass, so we're expecting that theta 1 should be equal to the critical angle because that's the one going in. And for the water, we expect at least at the critical angle theta 2 to be at 90 degrees, right? So we expect it to be going along there. So that would be 90 degrees. And so when we apply this formula, we can then find the critical angle, which is theta 1 roughly. So we can then say the sine of critical angle, which is this one here. So that's the one, right? And that will be equal to, we can say N2 sine 90. Sine 90 is 1, and so N2 over N1. And we know what that is. So that will be equal to 1.33 for the water, and for glass is 1.52 because this one is for the water because it wasn't in there, and this one here is for glass because it's in here, the glass. So we're looking at here, that point there, and that's 1.52. And now we can find the critical angle here. So we can say theta 2 critical angle will be sine to power minus 1, 1.33 over 1.52. And that critical angle then turn out to be, punch that into calculator, and you get 61 degrees, 0.0 degrees. So that's 61.0 degrees. So that is, so that meant that 45 degrees is less than 61 degrees. So we can then say 45 degrees because this is going in at 45 degrees here. It's less than the critical angle. It's less than the critical angle, which is 61 degrees. As a result, we're saying theta 1 is less than the theta of critical angle. And what we're going to get, we're going to get that. So the total internal reflection will not occur, because some light will refract out into the water. And so what we meant is that because it's less than the critical angle should be 61 degrees, but it's 45. So it won't go that way, it will go into the water and refract into the water. If it was 61, it will form the critical angle, and if it's bigger than 61, it will form complete total internal reflection. But some of them is going into the water. That's why it's 61, and it's not, we need it to be 61 to go parallel to the surface, and we need it to be bigger than 61 to go in completely into the glass, back into the glass, so you can get total internal reflection. But because it's 45, it's less than 61, it's going refracted into the water. So we're losing some light into the water. So we can say, so less light stays within the wind screen. So less light is detected at sensor Question 2.5. The refractive index of the windscreen glass can vary by a few percent across the thickness of the glass. Discuss how this variation may affect the path of the ray through the windscreen glass. So point number 1, light may change direction inside windscreen. Light may change direction at the windscreen boundary. Number 3, variation too small to deviate significantly within the windscreen, the internal effect. Number 4, variation may be too small to affect total internal reflection at A, without droplets. This is the boundary effect. The 5th point, variation too small to significantly affect transmission at A with droplets. Again, boundary effect. So any two of these will be fine. It's a difficult question, this one. So any two of these will be fine. So question 2.6. A different design has the LED and the detector. So this is the LED and that's the detector further apart. So they're now further apart now. The ray undergoes more reflection, so that's more reflection there, inside the windscreen, so that's a windscreen. Before reaching a detector, we now need to discuss two ways in which this different design affects the sensitivity of the sensor to the presence of water droplets. More sensitive because more likely to encounter or detect water drops, or will encounter more water drops. Bigger decrease in light intensity, so more sensitive to rain. 4, less sensitive because more likely to encounter imperfection in glass or on surface of glass or dirt on surface of glass. Any curvature effects will be greater, so may not hit the detector because it will deflect away. Light intensity reduced without presence of water. Greater absorption in windscreen due to greater path length. So any two, one from there, one from there, will be sufficient. That one or that one, that one or that one will be sufficient. So question 3, we've got a diagram of a white light source and a single slit with a green filter in front, and we've got the screen also further ahead, and we are to describe the pattern produced on the screen. Okay, so this is the pattern we will see on the screen, and the central maximum, which is that one here, with lower intensity maxima. Maxima is plural for maximum, so this is maxima because there's many of them. So these are lower intensity. The height is the intensity, how tall it is, and so these are the lower intensity, but they are smaller to the right and to the left. So that's what this is saying. So you would have to say the central maximum has lower intensity maxima on either side, on that side and on that side. The central maximum, which is this one, is twice as wide. So from there to there is twice that one and is twice that one than the other maxima. These are the maxima. Maxima means many maximum, and this is maxima as well. Question 3.2. The green filter is replaced with the red filter. Describe the change in the pattern produced on the screen. Well, first of all, we know what the visible colors are. We got red, orange, yellow, green, blue, indigo, and violet. This is arranged in terms of decreasing wavelength. So red has a longer wavelength than green, which has a shorter wavelength compared to red. So if I write the equation, which says that the fringe width is equal to the slit distance times lambda over the screen distance from the slit, and you can now see the relationship between the W, the fringe distance, which is directly proportional to the wavelength. So if W increases, the wavelength increases. That means if the wavelength increases, then the separation increases. Because we're replacing the green with red, we are increasing the wavelength, which means the separation will get wider. So the separation, so W, will get larger because we're increasing the wavelength from green to red. So we're gonna have a wider central maxima. So that means they get wider. Subsequent maxima further apart. So that means let's just say subsequent maxima will be further apart, and therefore we're gonna have a bigger wavelength, more diffraction. So let's just say that's 1, 2, and 3. Bigger wavelength, more diffraction. Question 3.3. A diffraction grating is placed between the red filter and the screen. The diffraction grating has 500 lines per millimeter. The light is incident normally on the grating as shown in the figure. Now what we need to do is it says calculate the angle of theta between the first order maximum and the central maximum. So what we've got is we've got 500 lines per millimeter. So that means per means, divided by, when we say milli, we meant 1 millimeter. Okay, so per means divide, but milli is basically 1 over, so that the first little m is basically 1 over 1,000. So I'm going to replace the first m with 1 over 1,000. The second m is meters. So I'm going to get 500 lines over 1 over 1,000 meters. So still got the meters at the bottom, and that is basically this number of lines. So that's L, the number of lines. All right, so let's just put the number there in the subscript. So L for line and number of line. And so now what we can do now is, well, 1 over 1, well, if I write this as 500 times 1 over 1 over 1,000, don't forget this is still 500 over m, that's the meters, and that should be equal to, well, 500 times 1,000 over meters. So that L, number of line, is basically 500,000 per meters, so per 1 meter. So now we want to find the meter. Meter is distance, that's distance between the two lines. So if you have so many lines like that, 500,000 of them, and you want to find the distance between the first two lines, that distance there, you're going to find that distance, and that's what we call D. Don't forget 500,000 lines, okay? So you have to work out 500,000 lines, and you will find out the distance between them. So the distance now, well, all equal distance, by the way. So that distance is going to be D, and that will become 1 over Ln. Because we got, so let's just write it down. Why is that? Because so that the m will come up to the top, and that's the meters. So if you write D will be equal to 1 over 500,000 over meters. Now you can see the meters will come up. So therefore D will be equal, well, 1 over 500,000 meters. And that makes sense, and that is 2 times 10 to the power minus 6 meters. So that's how we calculate the distance between the lines, and that's D. But now we need to apply the formula to find, because we have to find the angle theta. And so we have n lambda, that's the formula, equals D sine theta. So we want to find theta, so we can rearrange the equation by saying sine theta equals n lambda over d. And if I divide both sides by sine, so I'm going to get sine theta over sine equal to 1 over sine, because I'm dividing both sides by, and now I get n lambda over d. 1 over sine is basically sine to power minus 1. That's what you indices into bracket n lambda over d, and that will be what sine cancels sine, so I got theta. And now I could basically find theta. So theta would be sine to power minus 1, n is 1 times lambda, which is 650 times 10 to power minus 9, because it's nanometers, over d, which is 2 times 10 to power minus 6. So that's your theta. So if you plug that into your calculator, you would get 19 degrees. So that is the angle that it will be, 19 degrees. Question 3.4. In practice, they fail to transmit red light with wavelengths in the range 600 nanometer to 700 nanometer. Suggest how this affects the appearance of the maxima. Order will be wider. This is order n equals 2, 1, 0, and gets wider as order increases. So we can demonstrate by using Young's equation. So we know that n lambda equals to d sine theta will be 90 degrees, and so we could find for lambda nanometer and lambda 700 nanometer. So rearranging the equation, we can find n will be equal to d sine theta is 90, over lambda. So for 600 will be n equals, we know d because we already calculated that before, so that's 2 times 10 to power minus 6 sine 90 degrees. Sine 90 is 1 divided by 600 times 10 to power minus 9. And for 700 nanometer, we could use n to be equal to d sine theta over lambda. That would be n equal to 2 times 10 to power minus 6 sine 90 degrees over 700 times 10 to power minus 9. That's 700 nanometer. For lambda of 600 nanometers, n turned out to be 3.3. So we can only get up to the third order. And for n equals to 700 nanometer, n equals 2.86. So we can get up to second order. From the equation, n is directly proportional to d. So we can see that n is inversely proportional to wavelength. Well, if the wavelength goes up, then n will go down. So you can now see that when the wavelength goes up, n goes down. And when the wavelength goes down, n goes up. So gradually getting broader, more spread out for greater order maximum. So part of the third order maximum is suppressed at longer wavelength for theta greater than 90 degrees. And we can see here the wavelength here, 700 nanometer, is greater than 600 nanometer. But for 600 nanometer, we can see n of the order of third order. And for n here, which is longer wavelength, we can see only second order, and the third order is being suppressed at a long wavelength. Question 4.1. The catapult is designed so that the weight of the beam and the weight of the empty wooden box have no effect on the tension in the rope. Suggest how the pivot position achieves this. So point number 1, the center of mass of the beam and box is at the pivot. So that's point number 1. Point number 2, we say that the sum of moments is 0 at the center of mass, which is the pivot. So therefore, we can say that the total moment, the total clockwise moment, which is the weight of the box, must be equal to total anti-clockwise moment, which is the weight of the beam. So question 4.2, the stones in the counterweight have a total mass of 610 kilogram and the projectile weighs 250 newtons. Calculate the tension in the rope. So we've got to take moment about the pivot. So this point is the pivot here, and taking moment, we need to first of all work out the forces here. So this is the first force here, which is 250 newtons. And here's another force here, mass times acceleration due to gravity, or mass times gravitational field strength. And that one is the force here. And taking moment about here, we need to work out what tension this one plays. So this tension is going in that direction, which means there's another tension parallel to this one here. So that tension is also going in that direction, so it's going down. Now we can work it out by using SOHCAHTOA. So that's SOHCAHTOA, and SOHCAHTOA is sine of an angle theta, and this theta is 50, equals to the opposite here, and the hypotenuse here is the tension. So that's tension there. So we can say opposite over tension. And now we can find the opposite. And so the opposite will become T sine theta. But theta is 50 degrees. And we can say T sine 50 degrees. So we've got the tension coming down here. So that's the T sine 50 degrees plus 250 newtons. Right, so we can now say take moment. So we're going to take moment now about the pivot here, and in that case we need to apply the principle of conservation of moment. So applying principle of conservation of moment, which states that the total clockwise moment equals total anti-clockwise moment. And so let's look for the clockwise moment. So the one going in the clock direction, here's the one going in the clock direction. So I'm going from there to there. So that's a clockwise moment. And so that would be, so we're going to get 610 times 9.81, that's the force, times the distance, which is 1.5 meters. So that is the force times the distance. So that's the distance here. So moment is equal to force times distance. And that's what we're applying. Now I'm going to equate the clockwise moment to the total anti-clockwise moment. So that will be equal to, now the total anti-clockwise moment is basically this one here going to there. That's the anti-clockwise moment going in the opposite direction to clock. So that would be 250 times 4. So that would be 250 Newton times the distance, which is 4 meters, plus T sine 50, that's the force, times 4. So here it is. That's the weight or force times the distance, plus another one coming down. Apart from that, there's another one coming down which is parallel to that, so which is here, and that's T sine 50 degrees times 4. So this one now equals to 8976.15, and that equals to, that's 1000 plus T sine 50 times 4, so that would be 40 sine 50. So now to find T, what we need to do is 8976.15 minus 1000 and divide them by 4 sine 50 degrees. That would be equal to T. So that gives T to be equal to 2603 newtons. Roughly, so T will be equal to 2600 newtons. Question 4.3. We've got a projectile question and it's asking us to calculate the range. We need to ignore the air resistance. Okay, so here's the projectile path and this is the range and that's the height, the distance 7.5 meters from the ground, and this is the velocity 18 meters per second. First of all, what we need to look at in this case is to look at the vertical component, and then we then look at the horizontal component. For the vertical component, we always using SOVAT, and for SOVAT, we got a distance here, vertical distance 7.5 meters. Initial velocity will be 0 meters per second, because that's the velocity, vertical velocity. The 18 is the horizontal velocity. So you can see that 18 here will be the horizontal velocity. That's the arrow pointing horizontal, but what about the vertical velocity coming down there? So that's 0. And we look at the initial and final velocity, we don't know that. And the acceleration is 9.81 meters per second. And the time, so T is time and A is acceleration, and the time is what we're looking for. So in order to find the time, we would say that, let's do that here. So T would be, well, we can use SOVAT equation. S equals to UT plus a half AT squared. And therefore we know U is 0. So if that's 0, so that means S will be equal to a half AT squared. If I multiply both sides by 2, so I get 2S equals to AT squared. But A is G, which is gravitational field strength. So just bear that in mind, that A equals G. So now I can find T. So T squared equals 2S over G. And that implies that T equals square root 2S over G. So if I'm looking for T, I'll go T equals to square root 2 times 7.5 over 9.81, and that gives T to be 1.23 seconds. Now we can look at the horizontal component, which means the velocity is traveling, and we know V equals displacement over time, and we're looking for the displacement, which is a range, which is distance in this case. So I can say now that Vt equals x. So x will be equal to the velocity, which is 18 meters per second, times the time, which is 1.23, and that gives 22 meters. So therefore, the range that we're looking for is going to be x equals 22 meters. Question 4.4. In another release, the sling is adjusted so that a projectile of the same mass is released just before the wooden beam is vertical. The projectile is not released horizontally. We need to discuss the effect this change has on the range of the catapult. Right, so when it's released just before vertical, which meant that it will be going in that velocity up like that. So you go up, it's got an upward velocity. But if it's released horizontally, then it will go down. That velocity there, horizontal velocity. So it will go upward now, and then come to a maximum, and then it will start to come down. So therefore, instead of having this range, which is the range it had before, so that's the range before. So the new range will be now from, let's draw this down, now from there all the way to there. So you can see now the range is longer compared to that range. So compared to this range here. And so the extra bit is added to it before vertical. So this is a vertical bit here, and so that will be the extra bit added to the range. So that bit is added to the range. Now we can then write that the component of velocity will be upward. So that means it's going up in this direction. So that's the component of velocity there, going up. And that's number one. Number two is that the rock will spend more time, or spend longer, which is more time, in the air. And number three, time, t, will be longer. Also, number four, range will be longer. Question 5.1. We need to show that the initial kinetic energy of the test vehicle is 700 kilojoules. So we know that the velocity given is 110 kilometer per hour, and that is 110 times 1000, because K is 1000 meters, divided by 1 hour. 1 hour is 1 times 60 times 60, changing it to seconds, and that, when you compute that in your calculator, you get 30.56 meters per second. We're given the mass, M is 1.5 times 10 to the power 3 kilogram. Now for kinetic energy, KE is equal to a half mv squared. We now know that a half times 1.5 times 10 to the power 3 times the velocity, which is 30.56 all squared, and that will be equal to, again, if we compute that into a calculator, we will get 700,231.5 joules, and we can then give it that round it up to 700 kilojoules. So the kinetic energy is 700 kilojoules. So question 5.2, the test vehicle hits a steel safety barrier at an angle of 20 degrees. As shown in the diagram, we need to calculate the component of the momentum of the test vehicle in a direction along the line of safety barriers, along that line here. We need to give an appropriate unit for the answer. So the velocity this is approaching is the v, and that is 30.5.6 meters per second, and we need to calculate the velocity along here. So we got to draw this right angle triangle here, and we need to apply, because we got the adjacent and the hypotenuse, we'll be using cos 20 degrees, which is adjacent, which is v, over the hypotenuse, which is 30.56, and therefore v would be 30.56 cos 20 degrees. So now we know what v is, which is v horizontal, and now we need to use that for the momentum, and we know what momentum is. Momentum equals mass times velocity, and we know what the mass is, so we can say 1.5 times 10 to the power 3 times 30.56 cos 20 degrees, and that gives the momentum of 43075. Well, the mass is kilogram and the velocity is meters per second. So therefore, the momentum will be 4.3 times 10 to the power 4 kilogram meters per second. Question 5.3. Immediately after the collision, the test vehicle moves along the safety barrier with no change in its momentum in this direction. We need to show that the kinetic energy lost in the collision is about 82 kilojoules. Okay, the kinetic energy before collision is 700 kilojoules. We just worked that out. And the speed after collision, so v after collision, is we said is 30.56 cos 20 degrees, and that turned out to be 28.7 meters per second. And now we can work out the kinetic energy after collision. So the kinetic energy after collision, this is before, will be equal to a half mv squared. So in this case, we can say 1/2 times 1.5 times 10 to the power 3 for the mass times 28.7 squared, and that gives 618 kilojoules for the kinetic energy after collision. Now what we need to find is difference in energy. So the difference in energy, so change in kinetic energy, so that will be kinetic energy before collision minus kinetic energy after collision. So before collision is 700 minus kinetic energy after collision, which is 618, and that gives 82 kilojoules. So that's the change in kinetic energy. Question 5.4. The steel safety barrier deforms during the collision. The barrier to pass the test vehicle should not move more than 1.5 meters towards the other carriageway. The barrier can apply an average force of 16 kilonewtons at right angle to the carriageway. So that's at right angle there with that distance, and we got a force 60 kilonewtons. But we know that the work done, which is energy, and that is force times distance, and that work done is 82 kilojoules. So 82 kilojoules is what is done. But in order to move a distance by 1.5 meters, what energy is required? Well, the energy required for that would be, we got the energy required will be equal to force times distance, and that will be 60 kilonewtons times 1.5 meters, and that gave 90 kilojoules, because 60,000 times 1.5 is 90,000. So that's 90 kilojoules. So that is actual energy that is required to move by 1.5 meters. As you can see, we don't have that much energy, so that's the E required, but we don't have that. We only have 82 kilojoules. So what distance will you move by 82 kilojoules? Okay, why don't we work that out? So for 82 kilojoules, so we go 82 kilojoules will be equal to force times distance, and we know the force that it's applying is 60, right? So we can then say, well, the distance that it will move will be 82 kilojoules over 60 kilonewtons. Obviously the K cancel out, so you're going to get 0 cancel out, and the distance that it will move is 1.4 meters. So that is more than enough. It will not be able to move 1.5 meters, so that is safe. So we can then say that since it's not 1.5, so yes, the barrier is safe enough. Question 5.5. A different safety barrier uses a solid concrete wall which does not deform. The same standard test is carried out on a concrete wall. Discuss which type of barrier would cause less damage to the dummies in the test. Well, so increase time of contact as material deform. Then we go impulse. Impulse is force times time, and that is changing momentum, and which is changing mass times velocity. And that means that you need a small force. Increasing stopping distance as material deform. So increasing stopping distance as material deforms, then the work done will be equal to force times distance, which is S's distance in this case, and that implies a small force. But if we look at the barrier first, with concrete, no energy is transferred to the barrier if it does not deform. At the same time, it will be an elastic collision. Therefore, for an elastic collision, you're going to have change that will be equal to 2 times initial momentum. And because you're going that way, and then you come back again, so that's the wall, and therefore force will be change in momentum over time. So the force experienced will be greater. So the force experience will be greater because the time is small. So if the time is small, because force is inversely proportional to time, so if time is small, the force will be greater. Question 1.6. We need to state the time in milliseconds when P is moving at its maximum positive velocity. Well, the maximum positive velocity would not be here because that's negative velocity, because velocity is displacement over time. So that means the gradient is what we're looking for. So let's write that. So velocity is displacement over time, and so we're looking for the gradient, and we're going to find the time with the maximum gradient. So the maximum gradient is at 1.5. That's the time there. So positive, we want positive velocity maximum, so maximum velocity, and that occurred at t equals to 1.5 milliseconds because the unit here is milliseconds. So that's milliseconds. So that is the positive velocity, which is positive gradient. So that would be the positive maximum gradient because the gradient here, change in displacement over change in time, is the velocity. Question 6.2. Calculate the maximum acceleration of P. So A is equal to minus omega squared x because we're looking for magnitude of A. So I can say A equals omega squared x. And to find A maximum, we're looking for omega squared A, which is the amplitude here. So that's A. But omega is equal to 2 pi over t, and therefore A will equal to 2 pi over capital T squared times A. So now we can find A by saying A equals to 2 pi over t squared times 4.2 times 10 to the power minus 3. So the 4.2 is this 4.2 here. That's the amplitude. That's what A is, amplitude. We need to put the period in. Here's the period, which is 2 times 10 to the power minus 3. That's from there to there is 2. And that's 10 milliseconds, which is 10 to the power minus 3. So the value of A is 4.15 times 10 to the power minus 4 meters per second square. Question 6.3. The loudspeaker creates variation in pressure and produces a sound wave in the air around it. State the type of wave produced and describe the motion of the particle in this type of waves. So the type of wave produced in sound is longitudinal wave, and this is where particles oscillate or vibrate parallel to the direction of energy transfer. Question 7.1. Here the diagram shows a practical circuit in which a variable resistor is used to control the brightness of a lamp. And this is a lamp, and that's the variable resistor. The voltmeter reading is monitored as the variable resistor is adjusted to make the lamp brighter. So you're adjusting this to make the lamp brighter. Explain why the reading on the voltmeter decreases. So the reading on the voltmeter here, which is measuring the voltage across the resistor, the lamp, we need to explain why the reading on the voltmeter decreases as the brightness of the lamp increases. From the diagram here, here's the power supply. Most power supply have the internal resistance, and this EMF, this is EMF, that's the total power supply, that's where EMF is, and R is the internal resistance of the power supply, so that's the battery if you like. And V is called the terminal potential difference. Terminal PD, that's terminal potential difference, which is measured in voltage, in volts, and that's the voltage. V should be constant. It should be constant. If not, then it is due to the internal resistance. So V should be constant. If not, it's due to internal resistance changing. Therefore, terminal PD will decrease if the internal resistance increases. So what we're saying is that there's a relationship you can use. Voltage supply. Voltage is basically supplies the energy for the electron to move in this circuit. Electron comes from the negative terminal here, and current flows from the positive terminal. So if this one will have its own voltage, and that's called internal voltage due to the internal resistance here. And this is the terminal PD. So you can see now that the total energy supply or total voltage to the system is equal to the terminal PD here plus the internal voltage of the internal resistance. And so we can then make V the subject, the terminal PD, and therefore internal resistance at the total voltage supply, that's EMF, minus the voltage due to the internal resistance. And as you can see, if that increases, and this is constant, so if that increases, then that will decrease. Therefore, the terminal PD will decrease. Another way to look at it is to say that we know that the VR is equal to I times little r. So we also know that the terminal PD is equal to same I times big R. So this one is big R. And now, this is the big R here. So now if we take the ratio of these two, that over that, and we know that the i's will cancel out, and so we can say that the ratio of the voltage, internal resistance voltage, to the terminal PD will be equal to a constant, which is going to be R over big R. And that is a large ratio, because if the terminal PD decreases, if this decreases, then that will be big, because if this decreases, then that will be large. So we can say the brightness increases due to current increasing. Number 2, increase in voltage across internal resistance due to internal resistance increasing. That will cause the decrease in the voltage of the terminal PD. And number 3, the ratio of R and R, big R, is large. Question 7.2. The variable resistor is adjusted so that the lamp is at its brightest. So you're adjusting this to get the brightest for the lamp. The reading V1 on the voltmeter is noted. A second identical cell is then connected in parallel with the cell. The new reading V2 on the voltmeter is noted. So this is the second cell connected in parallel. We got new reading V2, and that's noted. We need to explain why V2 is greater than V1. So because we've connected the resistance in parallel, we need to find the total internal resistance. We can do that by saying 1 over R total internal resistance will be equal to 1 over R1 plus 1 over R2. Just so you know, this is R1, the internal resistance for that cell, and this is R2, the internal resistance for this cell. And so in doing that, we can find the common denominator, which is R1, R2. That means being multiplied, and this will then give you R2 plus R1. That's 1 over R total. So therefore R total is if you do reciprocal of both sides, you get R1, R2 over R2 plus R1. But we need to remember that R1 is equal to R2. So therefore, we can get R1 over R1 plus R1. And that will be R total. So R total will be R1 squared over 2R1. And R1 cancel both in the top and denominator, so you get R1 over 2. So that will be the R total. So this is what we call reduced internal resistance. So the R total is reduced internal resistance. And so what we will get is that if we look at for the first cell, the electromotive force is terminal PD plus I R1 for the internal resistance, and therefore terminal PD will be equal to electromotive force minus I R1. If we compare that with the second cell, where you have the electromotive force is equal to terminal PD plus I R1 over 2, because the total resistance is R1 over 2 here. The total resistance is R1 over 2, and therefore V, terminal PD, will be the electromotive force minus I R1 over 2. And so this one is V2, and this is V1 on this side here, that's V1. So you can see V1 is equal to electromotive force minus I R1. And now we can see from here that this is going to be half, and this is the same, and this is half. What that meant is this V2 will be bigger, because this is half. So V2 will be bigger. Unlike this one here, V1 will be less. So having the two internal resistance in parallel will decrease the internal resistance. Hence, the voltage the terminal PD will increase. So we can see that the reduced internal resistance is half, as you've done here, and therefore the voltage here increases, and lost volts reduced, therefore V2 is greater than V1. Question 8. The process of a beta plus decay can be represented by this Feynman diagram. Which row identify particle X and Y. So we have a proton being converted into a neutron here. So that's proton being converted into a neutron, and we need to find X and Y. So 1 plus 1, that's proton, mass and charge, going to 1 mass, 0 charge of a neutron, plus, well, if we balance it, so we're going to get plus 1, 0, that'll be beta plus electron neutrino. And we can now see that the weak interaction here is positive because you are making a positive beta. So that's positive because you got proton going, and so that's positive there. And also the electron neutrino. So this one is weak interaction and electron neutrino there. So the answer will be A from the table. Question 9. An electron collide with an isolated atom and raised an orbiting electron to a higher energy level. Which statement is correct? The correct statement here is that the energy from the colliding electron is being transferred to the orbiting electron. So basically the answer is D. The answer will be D, because an electron, so if you got a electron in a shell orbiting and another electron it's coming to strike that electron, and therefore the electron will be transferred energy, which then makes the electron go into higher orbital. So this is a higher orbital there. So that electron will then jump into higher orbital, because once gained the energy, it will be transferred into higher orbital. Question 10. Light of frequency, so let's call that F, frequency of light, is 2.0 times 10 to power 15 Hertz, is incident on a metal surface. The work function of the metal surface is, so a work function is equal to 4.6 times 10 to power minus 19 joules. Which statement is correct? Well, with this situation, it is always important to work out the energies here. So we know that E is equal to the work function plus the kinetic energy max. So we know that we've been given the frequency of light, and we know the Planck constant H. H is a Planck constant, which is 6.63 times 10 to power minus 34 joules second. And we know that E is equal to HF. So we can find, and we know the work function, so we can find the kinetic energy in this case. We can find the kinetic energy max. So the kinetic energy max will be equal to E minus work function. And so we have 4.6 times 10 to power minus 19 joules. That's the work function. So let's give that minus because that's the work function. And then E is plus, I better put plus there. So that would be H, the Planck constant, which is 6.63 times 10 to power minus 34, then times the frequency, which is 2.0 times 10 to power 15. And when we work that out together, 13.26 times 10 to power minus 19 minus 4.6 times 10 to power minus 19, and that gives 8.66 times 10 to power minus 19 joules. So that is the kinetic energy max. So that's K energy max. So from the answer given to us, we can see that the answer that is correct will be C, because that C value is given the kinetic energy max, and that's 8.7 times 10 to the power minus 19 joules. This value here is actually for that value, so that value is there, and that's why you got a minus here. And this value here, that's plus, that's for this one, which obviously I need to put that in bracket because that's calculating this value here. Question 11. We have a photon of ultraviolet radiation has a frequency of 1.5 times 10 to the power 15 Hertz. What is the momentum of the photon? So we know from Louis de Broglie that lambda is equal to h over p. P is the momentum, h is the Planck constant. This is Louis de Broglie in 1924. And we know that the basic equation for speed of light is c equals f lambda. And so we can make lambda the subject. So lambda equals c over f. So if we take that lambda and replace it here, and we can write that c over f is equal to h over p. What is the momentum of the photon? So we're looking for the momentum, and to do that we can say, well, momentum p will be equal to hf over c. So that's momentum, and we know what h is, 6.63 times 10 to the power minus 34 times the frequency we're given, which is 1.5 times 10 to the power 15, divide all by 3 times 10 to the power 8. That's the speed of light in a vacuum, and that gives 3.3 times 10 to the power minus 27 kilogram meters per second. And that's the momentum, because momentum P is mass times velocity, and mass is kilogram and velocity is meters per second. That's the unit there. So the momentum is that. Checking the answer, that will be C. Question 12. Which statement about a couple is not true? Well, it must consist of coplanar forces. That is true. It can produce rotation motion. That is true. It can't produce translational motion. That's not true. It has a momentum with unit Newton meter. That's true. So the answer is C. Coplanar forces is a force. One is going in that direction, and the other one is going in that direction. So it's a turning effect. It's not a translational motion. Translation motion is when you move along X or Y direction, or you move in a vertical Y direction like that. That's what you call translational motion. But the moment here is a turning effect, so it's force times perpendicular distance, and that is a turning effect. Question 13, we want to find that what is the distance between P and Q when T equals 8 seconds. Naturally, to find distance, X is the distance, and V is velocity, and T equals time. So we know that V equals X over T, and X equals to VT. But the area under the graph is the distance, because this is a velocity time graph. So let's work out the distance for P, which is, I'm going to find for P, I want to find the area here from 3 here. You see, from 3 the area. So I'm shading the area now. All right. So that area for P is going to be 20. That's the height. That's 20 over 2. So that'll be 20 times 2 over 2, because we're using a half base times height. So the 2 is the denominator, that's the base is 2 and height is 20. Plus, we also have the whole area, which is, I'm going to shade that one now. So this one here, that's the whole area for P. And that's between 3 and 8, and that's 5 for the base, and the height is 20. So that would be, it's a rectangle this time, not a triangle. So that would be 20 times 5. So if we add all together, we get 20 times 2 over 2, which is 20, plus 20 times 5, and that should be, that's 100 plus 20, so that's 120 meters. But we also need to find a distance for Q. Q distance will be, right, so where's Q? Q is the whole, so let's use the white here. So Q is the whole thing up to 8, and that's the whole thing. And so therefore it's a half base times height. So a half base times height, and the base is 8. So 0 to 8, that's 8 there. So that would be, that's 8 times the height is 40 over 2, and that gives, that's 4 times 40 That's 160 meters. So that's the distance for Q. And the difference, we need to find the distance between Q and P. So that would be dQ minus dP. And that would be 160 minus 120. And that is 40 meters. So the distance we're looking for is A. And that's 40 meters. That's A. Question 14. What is the upward acceleration of the 0.2 kilogram mass at the instant that the thread is cut? So first of all, we need to establish the tension minus 0.2 mass times the gravitational field strength, because the weight, tension is a force minus the force due to that mass. Hence, that equals the mass times acceleration. This is Newton's second law of motion, but the tension itself is the total mass of the system in this case. So that is 0.3 times 9.81 minus the 0.2 times 9.81 equals ma. So this is the tension, because that tension equals this total mass times the gravitational field strength. So that's that one. And that's 0.2 plus 0.1 times 9.81. And minus the mass of that and the gravitational field strength. Multiply. And that equals ma. So now we can write the common factor here is 9.81. So we get 0.3 minus 0.2 times 9.81 equals ma. And m in this case is 0.2. So we get 0.1 times 9.81 equals 0.2a. So that's the 0.2, because we're looking for the acceleration due to that when this is cut. And so we would have 0.1. So to find a is 0.1 times 9.81 over 0.2 equals a. And plug that into calculator. A equals 4.905 meters per second squared. So that's the value of A, 4.905 meters per second squared. And that answer is B. Question 15. A lift of a mass m, that m, is suspended from a cable. The lift descends with a downward acceleration. A frictional force F acts on the lift. What is the tension T in the cable? So to find the tension T in the cable, we can then say, because the mass, the lift is leading downward, which means the mass, the weight of the lift is leading. So we can say mg, that's the weight of the lift, minus tension minus frictional force will be equal to ma. We want to make tension the subject, so mg minus ma minus frictional force equals tension. Well, capital M is a common factor, so we go g minus a minus f equals to tension. So the tension will be equal to capital M into bracket g minus a minus f. So the answer will be D. Question 16. A body of constant mass falls freely due to gravity. The rate of change of momentum of the body is equal to its. Right. The rate of change of momentum, that is dp over dt, is equal to force. And this is Newton's second law of motion. Newton's second law of motion. And force, anything equal to force in the question, the only thing that is equal to force is weight, and that is D. Question 17. An electric vehicle is driven by a motor which produces a constant driving force. The vehicle travels from rest along a straight horizontal road. Friction and air resistance are negligible. Which statement describes the variation with time of the power developed by the motor? So A, it stays constant, not true. B, it increases linearly from 0, That's true. So the answer should be B. C, it increases non-linear from 0. And D, it increases from 0 to a maximum and then decreases. That's not true. So the answer is B. Question 18. Which is a correct statement about mechanical power? Well, mechanical power, P, is equal to energy over time, and energy is force times distance and then over time, but force is ma, that's mass times acceleration, and then times distance all over time. The unit for mass is kilogram, unit for acceleration is meter over second squared, and the unit for distance is meter as well, and then unit for t is seconds, so I just put seconds there. Therefore, unit for power will be kilogram meter squared over second cube, which can be written as kilogram meter squared per second cube. And the answer to that one is C. Question 19. A load of 50 newtons is suspended from a wire that has an area of cross-section of 1 millimeter squared. The stress in the wire in Pascal is between. This is stress, symbol for stress, and stress is force over area. And the force given to us is 50 newton, and the area is 1 millimeter squared. Milli is 1 over 1,000, so I'm replacing the m here by 1 over 1,000, so which is 1 over 1,000 squared, because this is squared, that square is for that, and that square is for that. And this is meter squared. So now I've changed the m into millimeter into meter squared. And so stress is 50 over 1 over 1 millionth, 1 million, and that's 10 to the power 3. 10 to the power 3 squared is a million. So what I'm saying is we go 50 over 1 over 10 to the power 3 squared, and that is newtons meter. And so that gives you, because that's 10 to the power 3, and that's 3 times 2, that's 6. And from then, that goes up to the top because it's a reciprocal, and therefore you get 5 times 10 to the power 7 newtons per meter squared. And that's between, because 10 to the power 7 is here, that's 10 to the power 6 and 10 to the power 9. So it's around here, 10 to the power 7. So the answer is C. Question 20. Which combination of properties will produce the smallest extension of a wire when the same tensile force is applied to the wire? So we have the Young's modulus, E equals to FL over A times the divided by the extension, and we make extension the subject, so we get and force is constant, so we take force out, and we have a L over AE. So if the extension decreases, then we would have the length would decrease and the area must increase and Young's modulus will increase. So we look at which gives us the increase in area, and Young's modulus is going to be D. So the answer is D, because we've got the area has increased by 2 and the E has increased by 4E. So those are the two, and therefore the answer will be D. Question 21. A rubber belt in an electrostatic machine has a width of 0.1 meter and moves with speed of 0.4 meter per second. Each square meter of a belt carries a charge coulomb. So each square meter, to get a square meter, we can work out that the width times V will be 0.1 meter times 0.4 meter over seconds, and that would be 0.04 meters squared per second. And that implies that the area here is 0.04 meter squared in 1 second. And that is actually being carried by according to the question, the charge. So the charge that will be carried will be equal to 0.04 charge, because that charge is charge meter squared per second. Therefore, the answer will be B. Question 22. Charged plates X and Y has a potential difference of 1.5 volts between them. Which particle gains 3.0 electron volt of kinetic energy when moving from Y to X? So we've got the potential difference, PD, is equal to 1.5 volts. And if the electron is 1, and then that implies that the potential difference is going to be 1.5 electron volts. And if that's for electron, for proton, which is positive, and that also will be 1.5 electron volts. For positron, which is a positive electron, again that's E plus, that's 1, again that will be equal to 1.5 electron volts. But for helium nucleus, which has got 2 positive charge, that would imply 2 times 1.5 electron volts, and that will be 3.0 electron volts. So that will be alpha particle D. So the answer for that one is D, alpha particle, which is helium nucleus. Question 23. The diagram shows part of a circuit and the current in this circuit. What is the potential difference between point P and Earth? So we need to calculate V1, the potential difference for V1. V1 will be I1 R1, this is R1, and V2 will be I1 plus I2 times R2, because the total current, this is I2, and this is a junction here, and using Kirchhoff's law, which is I going through there, that I is I1 plus I2, that's Kirchhoff's law. That would be 2 plus 4, and that equals 6 amps. So V2 is I times R2, and that would be 6 times 20. That is 120 volts. So that's 120 volts, and this is 20, and the total voltage is going to be 140 and 0. Because 20 plus 120, so that's 140. So the difference between the voltage will be 140 volts minus 0 volts, and that's 140 volts. And the answer is D. Question 24. A voltmeter has a resistance of 4 kilo ohms and reads 1.0 volt for every scale division on the meter. A power supply of EMF 20 volt and negligible internal resistance is connected across this voltmeter and a resistor in series. The voltmeter reads 2 divisions. What is the value of the resistor? So we got voltage to be 1 volt and R is 4 kilo ohms. This is R1, and the EMF, this is the EMF, which is 20 volts, so that's the EMF here, that's 20 volts, and internal resistance of that is 0, and so that means the terminal PD is fully 100% from the EMF. And so what we have now is to apply Ohm's law. So Ohm's law, and that says V equals IR. So for I has V1 over R1, because this one is V1 R1, and that's the same current that's flowing through this one here, so R2 as well. So therefore I is also equal to V2 over R2, which meant that the V1 over R1 is equal to V2 over R2. So we can say V1 over R1 equals V2 over R2. So we want to find R2. So we can just go R2 is R1 V2 over V1, and that equals R1 is 4 kilo ohms times V2 is 20, 18. So V2 is 18 because this one is 18 volts and this is 2 volts divided by V1, which is 2 volts. And so we can say R2 is equal to 4 kilo ohms times 9, and that would be 36 kilo ohms. So that's R2, 36 kilo ohms. If we check the answer is B. Question 25. Two cylindrical wires P and Q are of equal length and made of the same material. The diameter of P is greater than that of Q. P and Q are connected in series and the ends of this arrangement are connected to a power supply. Which two quantities are of the same for P and Q? So we can see here that the current will be flowing through that, so that will be I, and the same current will be flowing through there. So current will be the same, and because the resistivity, because the material are the same for P and Q, therefore their resistivity will be the same. Resistivity is resistance times area over length. Current and resistivity will be same. And the answer is B. Question 26. In the circuit below, the initial voltmeter reading is 0. The temperature of the negative temperature coefficient thermistor T is then increased. Which change in the circuit could result the voltmeter reading to be 0? A. Decrease in the resistance of R. If you decrease that one, increase in the resistance of R, decrease in the resistor of P, and increase in resistor of Q. So we know the voltage here and the voltage here are the same, therefore that voltage will be 0. If that voltage is 0, what we have is using V equals IR. So if we got the temperature of the thermistor, if that increases, the resistance of thermistor will decrease, and if the resistance of thermistor decreases, then the voltmeter of thermistor will decrease, because the voltage is directly proportional to the resistance. So if resistance decreases, voltage will decrease. Also, if the resistance of the resistor decreases, therefore the voltage of resistor will decrease. Again, applying the Ohm's law here. So the answer is going to be A. Question 27. An electric motor lifts a load of weight W through a vertical distance h in time t. The potential difference across the motor is V, and the current through it is I. What is the efficiency of the motor? So the efficiency is useful power out over total power in. The useful power out times 1 over total power in. And the useful power out is going to be the energy over time times 1 over power in. Total power in is I, VI. But energy is work done, which is the force times distance, H over T times 1 over VI. So therefore, efficiency is equal to the work done, or is the weight, times height over T VI. So the final answer will be WH over VIT. And that answer is going to be C. Question 28. An object of mass m moves in a circle of radius r. It completes n revolutions every second. What is the kinetic energy of the object? So we know the frequency is equal to n, and we know also that the kinetic energy of the object is a half mv squared. But we know that v in a circular motion is going to be r omega, and so therefore I can have kinetic energy to be a half m r squared omega squared. But the omega squared is going to be 2 pi f all squared, because omega is 2 pi f, but f is n, so we can write omega is 2 pi n, and omega squared is 4 pi squared n squared. Therefore, the kinetic energy will be equal to a half m. Now we got v squared, which is r squared, and omega squared is 4 pi squared n squared, which is 4 m pi squared r squared n squared over 2, and that will be 2 m pi squared n squared r squared, and that's the kinetic energy. And the answer here will be C. Question 29. The graph shows the variation of a displacement d with time t for a particle moving with simple harmonic motion for period t. Which graph shows the variation of kinetic energy of the particle with time t? So we have the displacement is a sine omega t, and to get the velocity we get v equals to d over dt. D is displacement, and that will be equal to, if we differentiate with respect to t, we're going to get a omega cos omega t, and that will be the velocity. And if you sketch velocity graphs, it will be starting from here back there to there, because it's a cosine graph, and this is time t. But for kinetic energy, we need to, kinetic energy Ke is a half mv squared, and so if we get that graph, the graph would be more of the positive, and so that's what the kinetic energy will be. And this is a half mv squared with respect to time t, and so that's what we would have, and the answer for this one from the graph is D. So the reason why this graph is positive is because when you square the velocity, you're going to get a slimmed down version of this graph. So more like this negative will become positive, so that will be flip up. So that's why you get that there, because the negative, if you square negative, you get positive, so that graph will flip up here, and that's why that's flip up like that. So that's where you get the kinetic energy, because kinetic energy is a half mv squared. So the v squared here is what you're plotting, and m over 2 is a constant, and that's why the graph looks like that. Question 30. Two pendulums A and B oscillate with a simple harmonic motion. The time period of A is 2 seconds, and the time period for B is 1.98 seconds. A and B are released in phase. What is the number of oscillations of A before A and B are next in phase? So we've got the time oscillation for A to be 2 seconds, and for time oscillation period for B is 1.98 seconds. Just oscillation is number of cycle in 1 second. Let's look for A and for B. We might need to try 99 times 2, and that is 198 seconds. And for B, we try 100 times 1.98, and that gives 198 seconds. So that's the time they meet together again, and therefore we're looking for, the answer is asking for A oscillation, and A is 99, so we have to go for C. Question 31. The frequency of oscillation of a vertical spring is F when the mass hanging from the spring is M. what is the relationship between F and M? So we got the mass and the spring. So when we pull the mass, we accelerate it, and in doing so, we will have something called the restoring force, which is trying to bring it back to equilibrium, and that equals to minus kx. And so the restoring force is equal to ma, which means minus kx equals to ma, but a equals to minus omega squared x. So if we write this properly, we can say that minus kx equals to m minus omega squared x, where x cancels x, and so we can, and minus cancels minus, and so we can write by saying k equals m omega squared. K over m equals omega squared, and then we can say, well, omega equals to root k over m. Omega itself is 2 pi f, where we can substitute that into the equation. So that's 2 pi f equals root k over m. And therefore, f equals to 1 over 2 pi root k over m. If that's the case, that implies that f is directly proportional to 1 over root m, or f is inversely proportional to root m, but root m is m to power a half. 1 over root m is m to power minus a half. Therefore, f is directly proportional to m to power minus a half, and therefore A will be the answer. Question 32. We've got a metal panel is driven to vibrate at different frequencies. The amplitude A of the vibration is measured at each frequency. The graph shows the variation of amplitude with driven frequency. The damping of the metal panel is increased without changing the mass of the panel. Which graph on the opposite page shows the variation of A with frequency with increased damping? For that, it's going to be D. So that's D, because the damping here at 100 frequency in hertz, and the damping, the A in millimeter, and this one has a at 1, roughly at 1. So you can see the damping there is roughly at 1, that's 1, and the damping will be roughly at not 1 but 0.5. So that's roughly at 0.5, and what gives us roughly at 0.5 is D. So the answer is D.